Hello, everybody. I'm going to do two quick angular momentum conservation problems. The first problem takes a person who's going to have their arms fully extended, tiny little feet, and they're going to be on a frictionless platform. And we're going to put masses on the ends of their hands. So these masses will make 10 kilograms each. And the separation between them, this distance L, will make it 1.6 meters. Then the mass of our person will make it 75 kilograms. Yeah, we're doing a very simple model of a person in this case. We want to give the disk a rotation. So let's go 15 radians per second initially. And all of this is our initial condition. And then we go to our final condition, which has the disk it's going to have our person maybe they're in bell bottoms. I don't know. But our person is going to bring their arms together so that the masses are on center with the body. All right, this means I still have two masses at 10 kilograms each, except their distance apart now has gone to 0. I still have the mass of the person. And what we'd like to determine is what is the new rotation speed. So all of this is our final setup. And our approach is going to be angular momentum conservation. And so our angular momentum conservation, you'll remember, starts off with the total around the center of mass is equal to 0, and our LA total is composed of the L center of mass plus the spin. And the one we care about now is the spin, which is equal to I omega. Since we're working in a frictionless regime, we know we can. The frictionless regime means no external torques. So we can set the initial equal to the final. Also notice in our example, the center of mass of the system doesn't change. It doesn't move. And that means that the L center of mass is equal to 0. The next example will show you the difference between the two. All right. So let's take our system, put in these assumptions, and I'm going to get the spin final has to equal the spin initial. To get that right. So that I get I final, omega final, which is what I'm looking for, is equal to I initial and omega initial. So omega final is just I initial over I final omega initial. So the great thing about this is that our units are immediately obvious. Whatever the units of I are going to cancel away, and we're going to be left with omega final and omega initial. Alrighty. So let's climb up to, see if I have room for the initial. So I initial up here at the initial condition is going to be given by a sum of many things. One, I'm going to have the moment of inertia of the body, whatever it's going to be. And then plus, I've got two masses, both of them an L over 2 squared, around the center of our rotation, around our axis of rotation, which is straight up the middle of this system and of this system. It's what omega is rotating around. Okay. So we have to go L over 2 away from that axis of rotation to start with. The final case, we have the I of the body and we've brought the two masses to a point where they are 0 distance away from the center of mass. I'm just putting the over 2 in there because it doesn't matter. All right. So we've got the two moment of inertias. I initial is the I of the body, plus 2ml over 4. And all this is just going to be I of the body. And omega initial. So I'm going to wind up with I of the body divided by the I of the body, which we haven't defined, and I'm hoping we don't need to, plus 1/2 the 10 kilogram masses. Oops, that should be squared. And the length of 1.6 squared. All this times our initial omega, which we put at 15 rads per second. And we can do a quick calculation. Omega final is I of the body plus 1.6 squared times 5. So I've got 12.8. And that's going to be in kilograms meters second, because that's the units of moment of inertia over I body times 15. So I could give us a number for I of the body, and if we want a number, we can just make it up. How about I of the body is just, we got 12, 15, let's just make it 13. It's probably more than that. 18 kilograms per meter squared. So we wind up with 18 plus 12.8 divided by 18 times 15, 1/seconds, 1/seconds. So that's going to equal plus 18. We're going to divide it by 18. We're going to multiply that by 15. And I get that the omega final is equal to 25.7 1/seconds. So in this quick example, when the person brings their arms in, they change their moment of inertia. I final is actually smaller than I initial, so we speed up. Okay, let's do another example. Same person on a disc, and I'm going to be looking top down now. There's a head, there's an outstretched arm, the other shoulder is just hanging the arm down. So I've got a person here, and what I want to do is pitch a ball at them. So there's a green ball with a velocity coming right at them. So again, we have no external torques. If it's frictionless, and now we're going to have both kinds of angular momentum. So let's get back to blue, and I'm going to write delta LA initial is going to equal delta LA final. So initially the person is at rest, so I'm going to get the L center of mass plus the spin initial, and then the L center of mass plus the spin. L is going to be final. So my final picture looks a little bit like the same as it was: person, shoulder, hand out, and the ball being caught. And with the ball being caught, we're now going to get a rotation. And let's find that. Okay. So, we've got the red pen out. In the initial situation, nothing is spinning about the center of mass. So the spin goes away. In the final situation, we're going to make it so the center of mass has not moved. So L center of mass has not moved. Doesn't mean an individual thing hasn't moved, and that's what we're going to talk about next. L center of mass is R from the axis to the center of mass. Yeah, vectors everywhere. So it's going to be the distance from the axis to the center of mass crossed into the momentum of whatever the object is. So in this case, we're going to look at the distance from the axis to center the person's head to where the ball is. And since we're here, let's define this arm length, L. We'll make L equal to, since it's half an arm length, 0.7, make it easy, 75. And the mass of the person will make 60 kilograms. And then the mass of the ball, we'll keep it significantly less than the mass of the person. Okay. So, back to blue. On the other side of the equation, we're left with just spin. So we need I and omega. And omega is going to be in the direction of whatever R cross P is. So, let's set up a coordinate system where this velocity, starting from the axis, that'll be y, that'll be x, and because there's only spin, we don't have to worry about it. the coordinate system. All we need to know is that the axis is about the person's head. So when the ball comes in and is caught, we got to do this cross product first. So we need to define R in terms of X and Y, or we can just deal with it in terms of the magnitudes. So let's take the magnitudes of both sides and make a note that when the person catches the ball, they're going to rotate counterclockwise. All right, that means I can do the center. This cross product can now be written as R P and then the sine of the angle between them. And here's the cool thing. We know the momentum is just doing its thing. I'm going to have to give that a speed right now. Velocity is fast enough to travel, but not terribly fast. So let's go 6 meters per second. Okay. The momentum then is just going to be mv. Oops, I'm sorry. I've got nonsense written down. What I wanted to get at was that the momentum is going to be mv, and that we don't need the vector on anymore. And we would have liked to have kept that v. And then we get sine theta. So our sine theta is going to be the angle between the two. But notice what sine theta gives us. Sine theta gives us the side opposite. So sine theta is going to break down to being the, well, let's pull off to the side so I can see it better. Sine of the angle is going to be composed of the side opposite, which is just going to be L over the hypotenuse, which is our R. So my sine theta comes in over here as L over R, and I haven't yet multiplied this by R. So nicely, this side of the equation, we're going to see the R's cancel, and I'm going to wind up with mass, the momentum, times the length of the person's arm. So we have I omega now to work on. The I looks like we just have the I of the body. So don't forget that this is initial and this is final. So my I is going to be I of the body, and we're going to add to it, oops, the length of the arm squared times the mass of the ball. Because that's what's come. That has what has come into it. Okay, so we wind up with eye of the body. Oops. And we want that to be omega final. And let's just assume that the eye of the body, let me just erase it, behaves like a solid disk. So the eye of the body is going to be 1/2 big mass of the body plus the width of the body squared. And then we're going to get our mass of the ball, the length of the arm squared, omega final. Then this is mass of the ball on the left-hand side. All this times omega final. And we have to carry all this underneath and flip. So omega final is equal to mass of the ball, velocity of the ball, the length of the arm, divided by 1/2 the mass of the person, the width of the person squared, well, kind of the half width, plus the mass of the ball, L squared. So we'll come up here and we'll redefine the mass of the person. Oh, we did. We already have it. At 60 kilograms. Okay, so the top is the mass of the ball, 2.3 kilograms. The velocity of the ball was given at 6 meters per second. And the length of the arm was given at 0.75 meters. Then down below we get 1/2 the mass of the person, which is 60 kilograms. We need the width. So the W of the person is going to be what? Maybe a foot. So 0.3 meters. So the width of the person is 0.3 meters squared plus the mass of the ball, 2.3 kilograms. Its velocity, 6 meters per second. And its distance from the center of rotation, which is just L squared, which is 0.75 squared. And that's meters. Now, I don't know how much confidence you have in your calculator, but I don't have a whole lot of confidence in mine. So let's see, 2.3 times 6 times 0.75 gives me a numerator of 10.35 kilograms meter squared over second. And then we're going to get the bottom. So I'm going to do 0.5 times 60 times 0.3 squared. And that's giving me 2.7 kilograms meters squared, plus the other term, 2.3 times 6 times 0.75, and that's getting me, times 0.75, I forgot it had to be squared. That's giving me 7.76 kilograms meters per second. So with 7.7, I can add to that 2.7, and then I can take the 10.35 and divide it by the answer. And I have a omega final, which is very close to 1, 0.989. And you'll notice from our units, we have kilograms in all of the pieces down below. I have meters squared in all the pieces down below. So I'm left with just 1 over second, which is the appropriate unit for omega. Rotating at that rotation speed, I'm not entirely surprised given the numbers are all point somethings, that we come up with something about 1. So those are our 2 examples.